So let's have a look. We're still doing body defences, but this particular session is going to be on immunological memory and autoimmunity. Immunological memory and autoimmunity. Okay. So what are we going to look at in this particular session? We're going to look at something which is called the clonal selection hypothesis, and that's kind of really important. I kind of need to see that when you're actually doing this assignment for me. I need to see that you understand the four major points of the clonal selection hypothesis. We're going to look specifically within the clonal selection hypothesis how we came up with explanations for what we call immunological memory. In other words, how does your immune system remember everything that it has encountered? How does your immune system remember every single pathogen that you have ever come into contact with? In theory, your immunological memory means that you remember it. So if I encountered a pathogen when I was 3, theoretically speaking, my immunological memory still recalls that event, which means that in theory I am still protected against that particular pathogen, in theory. Okay? And we'll explain how that relates to this. We'll also look at this concept, which is autoimmunity. Autoimmunity, in essence, is when your immune system goes wrong. One of the 4 aspects of this clonal selection hypothesis has in fact gone wrong, and that can have quite serious complications for a patient. It has serious implications for their health, and there are diseases and conditions that you will be aware of right now that are the direct result of when one of the 4 aspects of clonal selection has gone horribly wrong, and therefore it leaves the person vulnerable to autoimmune diseases. Is everybody okay so far? Everybody okay so far? Brilliant. So let's move on. The clonal selection hypothesis. Now this clonal selection hypothesis is absolutely stunning, because if you can look at this PowerPoint on Teams, and by the way it's all on Teams for you, you will see when you look down here at the dates that these guys came up with the clonal selection hypothesis in the 1950s. Now that's quite an incredible feat, because at that stage we didn't have the science to necessarily prove all aspects of this particular hypothesis. That's why they called it a hypothesis, because they were hypothesizing. They didn't know it existed exactly, because the science couldn't tell them that at this stage, but they said, we believe this is the way that your immune system works. These guys are uber clever, because they basically distilled how your immune system works into 4 key points. Literally 4 key points. This slide is uber important. This slide I need to see reflected in the work that you give back to me to mark, because this slide clearly shows that you understand that the clonal selection hypothesis is made up of 4 distinct but related concepts, and we're going to spend a little time right now going through them. Number 1. Number 1 says that each lymphocyte, I'm going to explain that in a second, that could be either what we call a B cell in your body or a T cell in your body, bears, and this is the important part, a single type of receptor with unique specificity on its surface. Okay, what do I mean by that? Okay, perhaps some new words here that you may not have seen before. A lymphocyte is a specific type of cell that has got everything to do with your immune system. So whenever you see that word lymphocyte, you know that we are talking about a classification of cell that only, repeat, only has one real function, and that is, it is the main cell involved in your immune system responses to pathogens. Everybody okay with that? So a lymphocyte is basically an immune cell. It's a cell which is responsible for the delivery of your immune system. You'll also see here, I mentioned 2 other cells, a B cell or a T cell. These cells are basically a specific type of lymphocyte. So a B cell and a T cell are literally lymphocytes. Now I also say here that these lymphocytes have a receptor on their surface, okay? So if I were to draw a B cell or a T cell, which is a specific type of lymphocyte, they would have a receptor on their surface. Here is the receptor on their surface. And they literally have hundreds of these receptors on their surface. What you will notice is that each receptor on the surface of this particular lymphocyte is identical. So they have receptors on their surface which are all identical. They don't have different receptors on their surface, they are all identical. Okay? If I were to draw another lymphocyte, and I'm going to draw it over here, this lymphocyte has a different type of receptor on its surface to this one. All of these receptors on this lymphocyte are identical. They're identical. Now, we've already looked at antibodies, and some of you may be looking at this and thinking, hey Dave, those receptors kind of look an awful lot like the Y shape of an antibody. And you'd be right. Because these receptors on the surface you can think of as basically being surface-mounted antibodies. Okay? Every single surface-mounted antibody on this particular lymphocyte is identical. Every single surface-mounted antibody on this one is identical. No two are alike. So you have almost an infinite number of these lymphocytes, all of which have a different type of surface-mounted antibody. What a concept. What a concept. Number two. These guys basically said for your immune system to be kicked into action, it basically had to meet a pathogen. Until it met a pathogen, what they said was your immune system does zip. It basically sits and waits. It doesn't do a damn thing. It just waits to see what is actually going to get into your body. Further to that, they said that the pathogen that breaks in has to basically bind to one of these receptors. So basically it said that receptor occupation on the surface of our lymphocyte is absolutely critical. If that does not happen, then your immune system will not be activated. Okay? So we've got these lymphocytes. B cells and T cells are just a category of lymphocytes. What we said that each lymphocyte that you have in your body has a surface-mounted receptor on it. This particular cell has surface-mounted receptors that are all unique to that particular lymphocyte. This one has surface-mounted receptors that are all identical to this lymphocyte. The second point here is saying that for your immune system to be kicked into action, you have to have a pathogen that will fit right here. Here is our pathogen. And as you know, our pathogens also have little lumps and bumps on their surface that we call antigen markers. This has to fit this before this becomes activated. In other words, your pathogen has to basically encounter your lymphocytes before your immune system will be kicked into action. Now, once it's been kicked into action, things start to happen really, really quickly. Because your immune system immediately starts to think, hang on a second, if one of these pathogens has got it, then basically there must be thousands more. I'm only a single cell. How can I possibly hope to defeat all of these pathogens on my own? So effectively, this cell gets a message from your immune system that says, hey man, you better start dividing, and you better start dividing fast. Because there's no way we can beat these pathogens unless you divide. Unless you divide. And when you divide, we basically mean that you're going to produce a clone army. An army of clones all related to this particular activated lymphocyte. And each one of those clones will have exactly the same receptors on its surface. So they are perfectly equipped to find more of those. That's number 3. Number 4, and this is a real doozy, okay? When you are born with an almost infinite, almost, but not quite, infinite number of these lymphocytes. And this kind of sounds a bit weird. So you produce a shed load of these lymphocytes, and we're going to see where they're stored. The problem is that in the production of all of these lymphocytes in your body, some of those lymphocytes will have surface-mounted receptors on them that will actually attach to your own cells in your body. Now that's kind of not a great thing, because you do not want to raise an army to defeat cells in your own body. So part of the process that these guys came up with, proposition number 4 in their hypothesis, was every single lymphocyte that has a surface-mounted receptor on it that could be activated by our own cells is deleted. We get rid of it. Your immune system literally reads them and says, yeah, we'll keep that one because that one could possibly help us with a pathogen. And we'll keep that one, and we'll keep that one, and we'll keep that one. Oh, hang on a minute. This one, this lymphocyte, has a surface-mounted receptor on it that would actually fit a cell in our liver. Don't want that one. I'm going to delete that one and get rid of it. And then I'm going to have a look at some more. And some more lymphocytes. Yeah, keep that one, keep that one. Oh, hang on a minute. Here is a lymphocyte that would cross-react with cells, attached to cells, that were in our nervous system. Don't want that one, because that would mean we would destroy our nervous system. So I delete it. So proposition number 4, really important one for later on, is that every single lymphocyte that could possibly bind to our own cells is deleted. Okay. Brilliant. Well done. So, now we know what their theory was, what their hypothesis was. Let's just do some basics. Where the hell are all these lymphocytes made? They are all made in your red bone marrow. Once they have been made in your red bone marrow, these lymphocytes basically all find their way to your lymph nodes. And that is where the majority of them will remain. So they're made in your bone marrow, and eventually they will enter your circulatory system, and they will migrate, and they will go to your lymph system. And that is where they will remain until they are activated. Between here and here and here, you will delete all of those lymphocytes that would cross-react with your own cells, which means, in theory, only the ones waiting for a pathogen will end up in your lymph nodes, in your lymphatic system. Now, I said before that we had these words B cell and T cell. Your B cells go direct to your lymph nodes. Your T cells mature in what we call your thymus gland, which is literally maybe just above your heart. It's quite big in teenagers and babies, and gradually over time it reduces in size. They mature here, and then they end up going into your lymphatic system, and also then are stored in your lymph nodes. Super duper. So, let's have a look at clonal selection in a little bit more detail. Okay? Clonal selection we can think of in 2 parts. Part 1 is a stunning concept. Your body, as you are developing inside mum, is basically already trying to predict every single pathogen that you may ever meet in your entire life. It's already producing lymphocytes with surface-mounted receptors that are basically being engineered so that if you ever encounter a pathogen, you have already got a lymphocyte ready and waiting to destroy it. What a concept. What a concept. Your body is predicting what an antigen might look like before it's even met it in the real world. Brilliant. And, as I've already mentioned, what we also are doing at that particular time is that we are deleting all of those lymphocytes that would cross-react and bind to our own cells, because we don't want that to happen. We don't want to raise an antibody army against the cell that we have in our own body, because that would destroy our own cells. So let's have a look at that concept. I've often used this slide to try and explain clonal deletion. I want us to imagine that each of these particular individuals actually aren't individuals in some respects, because they are all the same person, but they all have a slightly different expression on their face. I want you to think of each of these people as an individual B cell or lymphocyte. So we have now created a pool of lymphocytes. I want us to now look at their faces and imagine that each of these lymphocytes, this particular expression on their faces is fixed. I want you to imagine that this is their fixed expression, that this is their basic receptor. So their face represents their receptor. Okay? So in the process of clonal deletion, we want to get rid of all of those lymphocytes that would cross-react and attach to our own cells. So we're going to do that right now. We're going to say, look, I want to get rid of every single lymphocyte that I have in my body right now that would cross-react with my own body cell. I'm going to get rid of all the lymphocytes that have a receptor on their surface that would cross-react with one of my own cells. Let's say, for example, that the smiling faces are the lymphocytes that we want to get rid of. So, by way of example, okay, here's one we want to get rid of. There is one we want to get rid of. This is one we want to get rid of. That is one we want to get rid of. So is that one. So is this one. So is that one. Any more smiling faces? I guess it. There, in case I missed that one off, and there, that one off as well. So I have now deleted all of the lymphocytes that would attach to my own body cells and destroy them. What I have left are the ones that I want to keep, because in theory, these are now going to go to your lymph node, and they're going to remain in your lymph node waiting just in case a pathogen happens to get into your body. Each of their facial expressions represents that surface mounted receptor. So here is our lymphocyte, here is the expression. So this represents a cell, a lymphocyte. That expression represents that receptor that we want to keep. This one represents another lymphocyte. Here it is, okay? But this time the receptor on its surface looks like that. We want to keep these because these receptors might come in useful if we encounter a pathogen that fits those receptors. We get rid of every single lymphocyte that would stick to one of our own cells, because that would be disastrous. Okay? Brilliant. So we have now deleted every single one of our cells that basically would cross-react with a body cell. We've got rid of them. This is just another slide. We've kind of done that process already on here. Okay. So what's left? What's left? Now we've actually got rid of all of the smiling faces. What we have left are the actual lymphocytes that are a pool retained in your lymph nodes that would actually deal with a pathogen if it actually got into your body. They've not yet met a pathogen, so we actually call them the naive lymphocytes. They all are now waiting in the wings, waiting in your lymph nodes for that moment and that day when a pathogen actually gets into your body. So we've deleted every single one that would actually cross-react with your own body cell, and we're left with a massive pool of individual lymphocytes just waiting to see if a pathogen got into your body. And this is a really kind of useful slide because this is kind of the stuff that you would see in a biology textbook, and it actually goes through what I have just said. Here we have our original cell made in the bone marrow. Here we have all of the different types of lymphocytes that are made from that original cell. And if you look really carefully on Teams, when you look at this PowerPoint, you will see that the receptors on their surface all have a different shape. Clonal deletion. We get rid of every single lymphocyte that would cross-react with our own body cells. That could be cells in the brain, it could be cells in your liver, it could be cells in your skin, it could be cells in your bone marrow, it could be cells in your nervous system. We get rid of every single lymphocyte that would cross-react and match and bind onto one of your own cells. There they go. There they go. These were the smiling faces. We've got rid of them. What have we got left? We have got this left. We have got these lymphocytes with these receptors that your body is going to store in your lymph nodes. Here they are. Here they are. They're all stored in your lymph nodes. Up until this moment in time, they have never met a pathogen. You have just retained them on the basis that they might meet a pathogen if one breaks into your body. One day, along comes a pathogen. This pathogen will not fit that receptor, and it will not fit that receptor. And I want you to imagine there are millions of other lymphocytes in your lymph node. Okay? Millions of them. But it does meet and match with that one, and only that one. This now gets a message. We're not going to go into the detail of that, but suffice it to say, this gets a very important message, a text message, that basically says, look, you've met a pathogen. Because there's only one of you, you now need to divide. You now need to form a clone army. You now need to basically replicate yourself, because if one of these is in your body, the likelihood is there are thousands of others just like it. You're not going to be able to deal with all of these on your own. So you need to replicate, you need to divide, and you need to make a clone army. Here is our clone army. Every single one of these clones is identical to its parent. Every single one of these clones has a surface-mounted receptor on it which is identical to its parent, which means that every single one of these can destroy the pathogen that has got into your body. We call this stage clonal proliferation. Clonal proliferation. In other words, we make an army of cells here identical to the one that was originally activated by the pathogen. And that's kind of a really useful slide. It's kind of a really useful diagram. You could draw that as an explanation of the process and submit it in your report. It's a really great slide. So, let's just talk a little bit more about that word I introduced just before, clonal proliferation. Okay? We're now going to make thousands and thousands and thousands of clones of the original lymphocyte that was activated. Here they are, clones. Every single clone identical, every single clone identical to the actual parent that originally met the pathogen. Every single one identical. So let's have a look at this diagram, and this is another great diagram that you could use in your report because it kind of clearly shows some important concepts about clonal proliferation and what we get at the end of that process. Let's go back over here to the beginning again. Here is your bone marrow. Here are your original stem cells in your bone marrow. Your stem cells have produced a whole series of lymphocytes. Here they are. Each one of which has a different surface-mounted receptor on its surface. All of these have now ended up in your lymph system because we have already deleted all of those that would cross-react with your own body cells. One day, along comes a pathogen. Here it is. Here is our pathogen, right here. This pathogen has markers on its surface which are antigens. These antigen markers on the surface of this pathogen will not fit this one. They will not fit this one. They will not fit this one. They will not fit any other of your lymphocytes other than one. One single lymphocyte. The only one that will match that particular pathogen is here, number 2. Number 2 now gets a message. The message being, you now need to divide. You now need to form a clone army. On your own, you are not going to be enough to beat the thousands of these that have already also got into your body. You've just met one, but the likelihood is there are thousands and thousands and thousands, if not millions of these already in your body right now. So you need to divide, and you need to divide really fast. And that's exactly what happens. Can you see here? We now have, from here on, we now have proliferation. We are now going to divide to form our clone army. Here we go. This cell divides into 2, identical to its parent. These cells divide into 2, identical to this one, identical to its parent. And so on, and so on, and so on. In the end, and this is kind of really important, guys, in the end you end up with 2 types of lymphocytes at the end. Each one identical to the parent that was activated. You'll notice that one of them is called a memory cell, and we're going to go back and talk about those in a minute. The other cell that is produced is called a plasma cell, and we're going to talk about those respectively right now. This is the end game of clonal proliferation. In theory, all of these cells are the same, it's just that this cell will do something slightly different to this cell in the here and now, and I'll explain exactly what that is right now. Plasma cells. Plasma cells are basically antibody factories. These are the cells that your immune system has produced to deal with the here and now. I need a cell that can go into battle right now and produce antibodies to get rid of the pathogen that is already in your body. I can't afford to wait, it has to happen now. If I don't do it now, we are going to get seriously ill. So plasma cells produce literally thousands and thousands of antibodies a second. So they are literally forcing out antibodies, producing them from your lymph nodes. They go into your lymphatic system lymphatic system drains into your circulatory system, and you are now flooding your body with antibodies. Those antibodies are designed to stick to the surface of the pathogen that has basically broken into your body and disable it, because that's what an antibody will actually do. Every single antibody that is produced by a plasma cell is identical to the surface-mounted antibody that basically started this whole process off. So they are tooled up specifically to hunt and destroy the pathogen that got into your body. So plasma cells, what do you need to tell them? Everything you need to tell me about a plasma cell is on these two slides. So plasma cells are prolific producers of customized antibodies. In other words, the antibody that was on the surface of that original cell that met that first pathogen, every one of these is an antibody now, produced by those plasma cells. They are identical, these antibodies, to the surface-mounted receptor on that original lymphocyte. These protein factories we call rough endoplasmic reticulum. You just need to think of that as a protein-making factory, because we already know that antibodies are made of amino acids, therefore they are made of protein. Now, our plasma cells can't just make millions of these things immediately. First of all, we have to make the flipping plasma cell in the first place. So I'll just go back to this slide. This process here, to get to this end product, takes time. And time in this particular case can be measured in days. You are not going to be able to make these overnight. If this is the first time that you have met this particular pathogen, it's going to take you some time to make these plasma cells to go into battle. And that time frame is actually measured in days. We call this the primary response. If this is the first time you have met this particular pathogen, it's going to take several days for you to make your clone army, which is why you will feel kind of rough before you start to feel better. So the primary response is basically the first time that you've actually met this particular pathogen, the first time ever you've met it. And it takes time, days, for you to make all of these plasma cells. So in effect, you feel kind of rough before you start to feel better. Okay. Now, as well as producing those plasma cells that are going to go into battle, we're going to come back to that time scale in a second, you're also going to make another very important cell. This cell is called a memory cell. Let me go back, and let me show you that right here. Here we are producing our plasma cells. Here are all the antibodies that these plasma cells are producing, which go into your bloodstream. They're dealing with the here and now problem of a pathogen in your body. Here are our memory cells. You will see again that they have a surface-mounted receptor, which is identical to the antibodies, which is identical to the surface-mounted receptor of the original lymphocyte that met that pathogen. But memory cells do something slightly different. And this slide is uber important, because this slide and the following slides explain immunological memory. They explain immunological memory. Just like that phrase, an elephant never forgets, your immune system never forgets a pathogen. Okay? As well as dealing with the here and now, the fact that a pathogen has got into your body, your immune system lays down the foundations of your immunological memory. It works on the basis, and this is staggeringly good, it works on the basis that if this pathogen has got into your body once, there is a likelihood it's going to get back in again, sometime in the future. Sometime in the future, you might meet this pathogen again, in which case, we don't want to go through proliferation again. We want an army in reserve. We want the foundations of an army just waiting now in the wings, in theory, for the rest of your life, just in case you meet that pathogen again. Memory cells are the basis of our immunological memory. These are the cells that you lay down now that are going to stay in your immune system theoretically for the rest of your life, on the basis that sometime in the future, might be days, might be weeks, might be years, might be tens of years in the future, this very same pathogen might get into your body again. What a fantastic design. You literally make millions and millions and millions of these memory cells. They don't go into battle this time. They wait in the wings on the basis that they might have to go into battle sometime in the future. So your immunological memory after that primary exposure could last 20 years, it could last a lifetime. Which means, in theory, every single time I have met a pathogen and have got ill, I have made memory cells which have protected me if that pathogen were to ever come back again. Brilliant design, brilliant design. So those two slides, this one and this one, are super important. These are the slides that you need to reflect upon when you are producing your response to me, because this explains, these last two slides explain how we get our immunological memory, and that is critical in the piece of work that you're writing for me. These memory cells are responsible for what we call our secondary immune response. These memory cells are the basis of your immunological memory. They are going to stay in your lymph nodes for the rest of your life. They may never encounter that same pathogen again, but your body predicts that that opportunity might occur, which means better that we have an army in reserve than going through that whole primary response again. Let me show you the slide, and let me talk you through it, because this kind of categorises why those memory cells are super important. Boom. Let's say, for example, your immune system meets a pathogen X that has got into your body right here, maybe through a break in the skin. From here to here, the pathogen is basically winning. It's colonising your body. Round about here, it meets that one single, because don't forget this is the first time you've met this pathogen, it meets that one single lymphocyte with a surface-mounted receptor that is specific to that pathogen. There it is. There's the pathogen. It takes this long for you to make your clone army. It takes days for you to make your clone army. Your clone army is now going to start to produce thousands and thousands of antibodies. Here we go. So it takes this long to produce your clone army. Now you are starting to produce thousands and thousands and thousands of antibodies. All of these antibodies are now destroying that pathogen. You're winning. You're winning. After about 14 days, you've basically won the war. Now you are just literally mopping up the remaining pathogens in your body, and basically by day 28, you've won. The pathogen has been defeated. Those plasma cells that you have produced here have basically made all those antibodies and destroyed the pathogen. Let's just say you're super unlucky. Okay? You're super unlucky. And on day 28, or day 30 maybe, you meet that very same antigen, that very same pathogen all over again. Don't forget, at the end of this process, you have made a load of memory cells. waiting in the wings, not involved in this first reaction, but waiting in the wings on the basis that you just might meet this pathogen again. And unfortunately, you have. Can you now see the difference that this makes? Instead of it taking time, instead of it taking some time to produce your clone army and all those antibodies, look at this. Boom. Out of the ballpark. You produce so many antibodies so quickly from these memory cells, you don't even feel ill. So you've caught the pathogen again, but your immune system has overwhelmed it before it's even got off the beach. Before it's even had a chance to make you feel ill, you have produced so many antibodies that you have completely and utterly destroyed it before it's even made you ill. If you were to meet this in 280 days' time, you would get exactly the same response, because those memory cells produce your immunological memory, the foundations of your memory, which means that you are protected, in theory, for life. And I think that is an astounding way in which our immune system actually works, our primary and secondary response. Okay, we've got a couple of slides left where I want to talk about autoimmunity. Autoimmunity is where the fourth part of the clonal selection hypothesis does not work. You need to be very clear in your report that you understand that it's the fourth part of the clonal selection hypothesis that is now no longer working. If you remember, when we talked about deselection, we talked about removing all the lymphocytes that would potentially cross-react or attach to our own body cells and destroy them. An autoimmune disease is where that process has gone wrong, and you have left behind one or more of those lymphocytes that will attach to your own body cells and will therefore raise an antibody army and will therefore destroy them. In other words, you now create what we are calling autoantibodies, antibodies against yourself. What a horrible thing to think of. Our immune system is actually now going to cause us a disease. Our immune system is going to cause us a major problem because we didn't delete one or more of those lymphocytes when we should have. We made a mistake. We made a horrible mistake and we let one of them just simply go through. So, what's an autoimmune disease? This is where the body's immune system loses the ability to recognise the difference between our own cells and non-cells, meaning a pathogen. Your immune system sees one or more of your own body cells as a pathogen, and it now creates autoantibodies to actually destroy some specific, and they are specific, cells in your body. So when clonal deselection does not work, you end up with a lymphocyte that can therefore create antibodies against your own self. Once this happens, we have major problems because you cannot turn this antibody off without turning off your entire immune system. So the treatment for autoimmune diseases brings with it major consequences, because to get rid of this, you also have to get rid of your normal working immune system. Okay. So, what do we see? I'm sure people have heard of multiple sclerosis. Did you know that multiple sclerosis was an autoimmune disease? It is where you have left behind one of those lymphocytes that you should have deleted. The surface-mounted receptor on this particular lymphocyte will attach, cross-react with the cells that make up what we call the myelin sheath, which is the insulation around your nerves. Over time, the antibodies that you are now producing will destroy all of this insulation, mistakenly believing that these cells that form the insulation are a pathogen, and they will destroy that insulation. The resulting effect is that we get multiple sclerosis. Multiple sclerosis, there is no cure. For the vast majority of autoimmune diseases, there is no cure. All we can do is suppress your immune system. And in suppressing your entire immune system, that makes you incredibly vulnerable to pathogens coming in from the outside. But there is no cure. We can just suppress symptoms. Rheumatoid arthritis, similar again. You now produce autoantibodies against the cartilage in the joints, causing major inflammation in the joints, mainly the synovial joints, in your body. Again, can we cure this? No. Can we suppress the symptoms? Yes. Okay? And if you think about it, autobodies. If we do not get rid and delete all of those lymphocytes that cross-react with our own cells, we will literally destroy parts of our body. So autoimmune diseases, you need to link it back to key point number 4 on the clonal selection hypothesis, and you need to be very clear that the reason why we have these diseases is effectively because we got clonal deselection wrong. Is everybody okay? We'll take questions at the end.